Welcome to the deep dive. Today we're getting into the SAIL-VL2 technical report. This comes from the Do-In SAIL team working with the LVNUS lab.
That's right.
Now, if you follow large vision language models, LVMs, you know it's often felt like a race for just bigger and bigger models. But SAIL-VL2, which follows up on SAIL-VL, seems to be pushing back on that a bit, changing the story.
Yeah, they really are. They're fundamentally questioning if just scaling up parameters, that sort of brute force approach, is the only way forward.
Okay.
Their whole philosophy, it's right in the report, is about how knowledge can be effectively injected through efficient architectures and training. It boils down to this idea about small models, strong performance.
Small models, strong performance. And they seem to have the results to back that up, right? It's not just theoretical.
Oh, absolutely not. The scale is quite something. They've tested SAIL-VL2 across, believe it or not, 106 different data sets.
Wow, 106.
Yeah. And they're hitting state-of-the-art results at both the 2 billion and 8 billion parameter sizes. So it shows efficiency doesn't have to mean sacrificing capability, especially on, tough tasks like reasoning or understanding complex documents.
Okay, so if it's not just about size, what are they doing differently? The report seems to point to three core innovations driving this.
That's a good summary. First, there's a very careful, large-scale data curation pipeline. Second, a really methodical, progressive training framework.
Right.
And third, some clever architectural moves, including using sparse mixture of experts or MOE designs.
Let's dig into that architecture first, the foundation.
Okay, so the basic structure will sound familiar. A vision encoder, then an adapter to connect things, and finally the large language model backbone.
Standard components.
Standard components, but crucially, each one is sort of tailored for efficiency here. They use their own vision encoder called SAIL-ViT.
Okay.
That connects via a pretty lightweight two-layer MLP adapter to the LLM, and for the LLM, they're using the Qwen 3 series.
And the report details specific configurations. Table 1, I think.
It does. They offer a couple of dense models. There's SAIL-VL2 2B, which comes in at about 2.6 billion total parameters.
So pretty compact.
Relatively, yeah. Then there's the SAIL-VL2 8B, scaling up to 8.8 billion parameters. Still competitive, not astronomical.
But then there's the MOE version, which sounds really interesting from an efficiency standpoint.
That's the SAIL-VL2 30B A3B. And this is where the sparse idea comes in. It has a huge potential capacity, 31.1 billion parameters in total.
Huge.
But, and this is the key, during actual use, during inference, it only activates and computes on about 3 billion of those parameters.
So you get the knowledge potential of a massive model, but the computational cost of something much smaller.
That's the idea. Massive capability, manageable cost.
And that vision encoder, SAIL-ViT, seems pretty central to making this work. It's not just any off-the-shelf ViT.
No, it's specifically tailored. It's a vision transformer designed to bridge that gap, the inherent difference between visual information and language tokens. It needs help to understand images in a way the language model can process.
And they even have a special variant of it, SAIL-ViT NRS.
Yes, the NRS variant is quite neat. It lets the model handle input images at, well, basically arbitrary resolutions, all the way up to a massive 1792 by 1792 pixels.
Okay, 1792 by 1792. Why is that high resolution so important for you, the listener, to note?
Well, think about the tasks you might give an LVM. Reading tiny text on a complex diagram, or understanding subtle details in a medical image, or pinpointing a specific object in a crowded scene for visual grounding.
Right, fine details matter.
Exactly. High resolution is often critical for the model to actually see those small but important elements, and they show it works. It gets a strong score, 57.82, on a visual grounding task called ref-co-co-fg. That means it's good at finding the thing you described in the text within the image.
That efficiency theme pops up again with the sparse MOE architecture you mentioned earlier. Can we unpack that a bit more? How does MOE work here?
Sure. So in a standard transformer, you have these MLP layers, kind of dense blocks of computation. In a MOE model, you replace those monolithic blocks with a set of parallel, smaller expert networks. Think of them as specialists.
Okay.
And there's a gating mechanism, like a router, that decides for each bit of input data, each token, which one or two experts are best suited to handle it. So instead of running all the computation all the time,
it only activates the relevant specialists.
Precisely. So out of that huge 31.1 billion parameter potential in the MOE model, only a small fraction, maybe 3 billion active parameters, are actually doing the work for any given input. It's based on the MOE design used in the Qwen 3 LLMs.
Sounds efficient, but also complex to get right. Does the report show this custom SAIL-VT actually helps align the visual and text parts effectively?
It does offer some quantitative evidence, yes. They measured how well SAIL-ViT aligns the visual features with the text features compared to a baseline model, AIMV2.
How did they measure that?
They used metrics like average nearest neighbor distance and, importantly, the Wasserstein distance. Basically, these metrics measure the distance or difference between the visual information space and the language information space.
And SAIL-VT reduced this distance.
Significantly, yes. A lower Wasserstein distance means the visual features produced by SAIL-VT are, let's say, much closer or more compatible with the text features the LLM understands. It makes the communication between the vision and language parts much smoother.
That alignment is obviously crucial, and it probably leads right into their training strategy, which you mentioned was progressive.
It does. The training for SAIL-VT is done in 3 distinct stages, sort of gradually teaching the model.
Okay, stage 1.
Stage I is called warm-up adaptation. Here, they keep the main LLM and the vision encoder frozen. Only that small, lightweight MLP adapter gets trained.
And the data.
Relatively simple stuff, about 8 million examples, mostly basic image captioning and optical character recognition, OCR. The goal is just coarse alignment, getting the vision and language parts roughly acquainted.
Okay, basic handshake. And stage 2.
Stage 2 is fine-grained alignment. Now, they unfreeze the vision encoder, SAIL-ViT, and the adapter, but the main LLM backbone is still kept fixed.
And the data gets more complex.
Much more. They bring in richer data like video caption pairs, which adds a temporal dimension, and also more advanced OCR datasets like docstruct for understanding document layouts. This pushes for a much deeper, more detailed alignment.
Makes sense. And the final stage, stage 3, is where it all comes together.
Stage 3, world knowledge injection. Now everything is unlocked, encoder, adapter, and the LLM. This is where they flood the model with broad knowledge.
How much data are we talking?
A huge amount, 36.5 million diverse data points. This includes everything from complex question answering and math reasoning problems to just pure text corpora to build general knowledge. The goal is broad understanding and reasoning ability.
That 36.5 million figure sounds impressive, but you also mentioned their focus on data curation. This brings us to SAIL Caption 2. Seems like they didn't just scrape data indiscriminately.
No, definitely not. This is key to their efficiency argument. They developed a pretty sophisticated filtering strategy using a specialized judge model to assess the quality of image caption pairs.
A judge model. How did that work?
It evaluated captions from 2 main angles. First, visual information richness, or VIR. Basically, how much useful detail is in the caption. Does it mention diverse objects? Does it capture visual complexity?
Okay, so is the caption descriptive?
Right. And the second angle was image-text alignment, or ITA. Does the caption actually match the image accurately? Is it specific? Is it complete? Does it hallucinate things that aren't there?
So quality control on 2 fronts. What was the impact of this filtering?
It was substantial. They started with a raw data set of about 300 million image caption pairs. Their judge model estimated that something like 15 to 20% of those captions were below an acceptable quality threshold. They used a score threshold of 3 out of 5.
So a significant chunk was just not good enough.
Yeah, potentially noisy or misleading data. By filtering that out, they distilled the data set down to 250 million high-quality pairs. They deliberately traded sheer volume for higher quality. It's a core part of that small model, strong performance idea. Better data means more efficient learning.
And this efficiency focus even extended to the training process itself. You mentioned ADLRS.
Right. Within their pre-training recipe, which had a couple of substages, they used a technique called ADLRS, adaptive learning rate search, particularly in the first basic pre-training stage.
Adaptive learning rate search. Sounds technical. Can you simplify that?
Think of training like tuning a radio. The learning rate is how quickly you turn the dial. A fixed learning rate is like turning the dial at a constant speed. You might fly past the right station or take ages to get there. ADLRS is like having the radio automatically adjust how fast you turn the dial based on how close you are to a clear signal.
Yeah.
It looks at the loss slope, how fast the model's error is changing. If the error is dropping quickly, it might slow down the learning rate to fine-tune. If progress stalls, it might speed up a bit.
So it finds the optimal learning rate more efficiently during training.
That's the goal. It helps converge faster and potentially reach a better final model state without as much manual tuning or wasted computation.
All this careful architecture, data curation, and training leads to some impressive capabilities, especially in reasoning. Let's talk about SAIL-VL2 thinking.
Right. This is a specialized version they developed specifically to tackle complex reasoning that requires multiple steps, sort of like thinking things through.
How do they trade for that?
They use what they call a thinking fusion SFT-RL hybrid pipeline. Bit of a mouthful.
Yeah.
It basically combines two main techniques. First, long chain of thought supervised fine-tuning, long hot SFT. And second, multiple stages of reinforcement learning, RLA, using different kinds of rewards.
Okay, long-caught SFT. Chain of thought prompting helps models show their work. How is long-caught different?
It specifically targets problems needing longer, more intricate chains of reasoning. Standard COT might be a few steps. Long COT aims for more complex, interconnected thought processes. They created a special data set for this 400,000 examples designed to teach these longer reasoning paths.
And they standardize the output.
Yeah, they use specific tags. Think to enclose the step-by-step reasoning process, and box to clearly mark the final answer. It teaches the model not just to reason, but to structure and present that reasoning clearly.
And the ultimate goal here was to match bigger models on reasoning tasks.
That was the ambition, and the results are quite striking. On the OpenCompass reasoning benchmarks, the SAIL-VL2 8B thinking model, the dense 8B version fine-tuned this way, actually achieved the top score among open-source models at 54.4.
State-of-the-art for its size. But what about the MOE version, the sparse one?
This is where the efficiency story really shines. The SAIL-VL2 Mo thinking model, remember, the one with 31 billion total parameters but only activating about 3 billion, scored 53.6 on the same reasoning benchmarks.
Wow, so nearly the same reasoning performance as the dense 8B model, but using significantly less active computation.
That's the takeaway. It demonstrates that you can achieve very high-level complex reasoning with a sparse architecture, provided you have the right training, like this thinking fusion approach. It challenges the need for purely dense models for top-tier reasoning.
Beyond just reasoning, how did the models perform generally?
They performed very well across the board, especially for their size classes. The smaller SAIL-VL2 2B model, for instance, hit state-of-the-art among models under 4 billion parameters on general benchmarks like MMBench V1.1 scoring 86.77 and OCR Bench 89.50. So strong general understanding even at the 2B scale.
And the 8B model excelled in specific areas.
Yes, particularly in document understanding. It achieved a score of 95.28 on DocVQA, which is about question answering on documents. That really set it apart among models in the 8B parameter range.
Were these capabilities limited to single static images?
Not at all. The report shows strong results for multi-image understanding and also for video comprehension. They performed well on benchmarks like Long Video Bench, which tests understanding of longer videos, and also on MMIU for tasks involving reasoning across multiple images.
And you mentioned one more innovation, more on the engineering side. Stream packing.
Ah, yes, stream packing. This was an infrastructure technique they used during training. It sounds technical, but the impact was significant. They found it accelerated the training process by about 50%.
50% faster training. That's huge.
It is, and it also improved how efficiently they used the GPUs, the SM utilization. But interestingly, it wasn't just about speed.
Oh, how else did it help?
By packing data streams more efficiently, it helped reduce sequence truncation. That's when you have to cut off long inputs because they don't fit. Less truncation means the model sees more context.
Which should lead to better performance on tasks needing that context.
Right. And they found this engineering improvement actually translated into better scores on open-ended question-answering benchmarks, likely because the model retained more of the necessary information from longer sequences. So engineering efficiency directly boosted model quality.
So pulling this all together, what's the big picture message from the SAIL-VL2 report?
I think the core message is a confirmation that significant leaps in LVM performance don't have to come from just making models unimaginably large anymore.
Yeah.
Instead, meticulous engineering, really rigorous data curation, like that VIRTA filtering removing 15–20% noise, and these smart progressive training strategies are becoming incredibly powerful levers. You could almost say these are the new scaling laws. Quality and strategy can rival sheer size, and the results speak for themselves. State-of-the-art across 106 benchmarks, and that SAIL-VL2 2B model ranking #1 on OpenCompass for models under 3 billion parameters. It's quite an achievement for that size.
It really is, and it leaves us with a fascinating thought, especially regarding that MOE reasoning model.
Go on.
Well, if you can get top-tier reasoning performance, nearly matching an 8B dense model by activating only 3 billion parameters in a sparse architecture, It really makes you question the necessity of always deploying these enormous, computationally expensive, dense models for every task.
Right.
SAIL-VL2 strongly suggests that with clever design and targeted training, you can achieve remarkable complexity and performance with much more efficient computation. That performance versus efficiency trade-off might be shifting significantly.